Swayam Prabha. Digital India. Educated India.
So, the first application. So, any questions about the theorem or its proof? So, one very crucial point about this theorem is that this theorem only gives a lower bound on a function over the De Morgan's basis. Okay, so, this is very crucial. So, when we are using this inductive argument, okay, we are very crucially using that the gates that are present are just AND, OR and NOT gates, and in fact, we are not even counting the NOT gates. NOT gates can be arbitrary, but we are counting just the AND and OR gates in that circuit. Over any other basis, this theorem will not hold. Okay. So, and we will come to this point a little bit later. So, let us consider a function, let us consider the parity function. So, consider parity of x1 up to xn. Okay. So, how is the parity function? Let me just define it once again. So, parity of x1 to xn is equal to 1 if sigma xi is congruent to 1 mod 2 and it is equal to 0 otherwise. Okay. So, how can I give a lower bound on the formula size of the parity function using Kravchenko's theorem? So, to give a lower bound, I have to suitably choose A and B. Okay, I have to suitably choose A and B, and now once I have chosen A and B, I can use the theorem. Okay. So, what I will choose is that, so let A be, in fact, I will choose A to be all inputs which map to 0, sigma in 0 1 to the power n such that parity of sigma maps to 0, and I will choose B to be all inputs in the same domain which map to 1. Okay. So, what can I say about the size of A? How many inputs go to 0? Huh? 2 to the n minus 1. Okay. So, there are 2 to the power n many inputs, half of them go to 0, half of them go to 1, right. So, okay. So, this thing is settled. Now, what can I say about n a comma b? How many tuples are there which are neighbors? So, how do you answer? I mean, how do you think? So, if for any set a comma b, if let us say someone poses this question, how do you think about it? Okay. So, the way you should think is that consider any string, let us say in A. Okay. How many neighbors will that string have which belong to B? Okay. So, let sigma belong to A. How many neighbors will it have which belong to B? n, because I can take any bit of sigma, and if I flip that bit, the parity changes, and because the parity changes, it goes to B. So let sigma in A, the number of neighbors of sigma in B is n. So therefore, what can I say about, and this is basically true for each sigma, okay, for each sigma this is true, each sigma in A. So therefore, NAB is equal to size of A times n, and I can give the same result for B as well. I mean, anyway, A, size of A and B are the same, so therefore it follows. So now what does Krapchenko's theorem give us? So by Krapchen, they need not be different, they can be the same. You mean the B's? I am looking at tuples, the tuple is different, right. So it is all pairs sigma comma tau. So I am fixing a sigma for which I have n many taus. Now there are 2 to the power n minus 1 many sigmas, right. Of course, some of those taus will repeat, but the sigma is different. So this is greater than n times A, n times, I can write it as B divided by A times B, which is equal to n square. Okay. So this says that if we look at the parity function, we need a formula of size at least n square over AND OR and NOT gates for this formula, okay, for this function. Now let us look at another example. Another famous function is the majority function. So majority of x1 to xn is equal to 1 if sigma xi is greater than or equal to n by 2 and it is equal to 0 otherwise. So if at least, I mean if the sum is at least n by 2, then the input is mapped to 1, otherwise it is mapped to 0. So what can we say about the formula size of majority? Now how do we choose A and B? Okay, so actually if you choose A and B nicely, then the problem is almost solved. Okay. So how do you choose A and B? Any guesses? So the idea is you have to choose A and B in such a way so that this, if I look at NAB, that is if I look at these tuples, that quantity should be maximized. Okay. I mean I have to choose A and B. Okay. So that is the idea. So and how do you maximize NAB? It is when you have an A and shifting just one bit of A or flipping just one bit of A would send it to B, right. So what would such an A be in this case? Huh? So just less than half many ones, right. So A is something which should go to 0. So if I have n by 2 minus 1 many ones in that string, then flipping 1 0 to a 1 would send it to B, correct. And what should B be? n by, no, B will be exactly n by 2 many ones, right, because just changing 1 1 to a 0 would send it to A. Okay. So, it is kind of so these two sets are like on the borderline. Okay. So, changing one bit of A string from A is sending it to B, and from B changing one bit to 0 would send it to A. Okay. So, these are kind of like the borderline sets. So, that is the intuition, that is how these sets should be thought about. Okay. So, I mean it might seem like it is kind of, I mean initially it might seem like magic that how these sets are picked, but I mean once you understand what is going on, it is quite intuitive as to how these sets should be picked. Okay. So, we will pick A to be all strings over here such that sigma has n by 2 minus 1 many ones. Okay. So, if it has n by 2 minus 1 many ones, clearly it is mapped to 0, and that is what we have, and B is all, let us say tau n 0 1 to the power n such that tau has n by 2 many 1. If it has half many ones, then by definition it is mapped to 1, correct. Now, let us count the, sorry, this is B. Okay. Now, let us count NAB. So, for a sigma belonging to A, okay, how many neighbors does it have which belong to B? We can make any of the zeros. So, if I flip any of the 0 to a 1, then it becomes an element of B. How many 0 does sigma have? N by 2 plus 1. If it has n by 2 minus 1 ones, then it has n by 2 plus 1 many zeros. So, for a sigma belonging to A, it has n by 2 plus 1 neighbors in B. Okay. I can take any of the zeros and flip it to 1, and for tau belonging to B, how many neighbors does it have in A? N by 2, because any of the zeros I can, sorry, any of the ones I can make it into a 0 and it would go to A. It has n by 2 neighbors in A. Okay. So, can you guess what the lower bound would be? What is the lower bound? So, NAB is equal to A times n by 2 plus 1, also it is equal to B times n by 2. So, therefore, L star of majority is greater than n square by 4. So, it is greater than n by 2 plus 1 into n by 2, which is greater than n square by 4. So, this is a lower bound on the formula size. So, similarly many other functions, for many other functions you can give a lower bound using this formula. So, any questions? Higher than polynomial lower bound, not that I know. For a fixed A. Yeah. So, once you fix an element in A or B, it can have only a maximum of n neighbors. So, getting better than quadratic is not possible. Yeah. Correct. Okay. Yeah, that is a good point. Okay. So, now what happens if we consider arbitrary basis? Okay. So, here as I said that Kravchenko's theorem crucially depends on the fact that the basis is the De Morgan's basis. Now, what happens if we go to let us say B2? Okay. So, how can we give a lower bound on the formula size of a function over B2? So, this brings us to another very interesting result. Okay. So, this result was due to a Russian mathematician Nechiporak, and he showed that you can actually consider, I mean you can actually give similar type of lower bounds for even arbitrary basis. Okay. So, here we will just prove it for B2, but if you just think about it, it can be extended to any B k for that matter. Okay. So, just to recall, so B2 is the basis of all functions over 2 inputs. Okay. So, B2 will have a total of 16 gates. So, before getting into Nechiporak's theorem, we have to define a few things. Okay. So, it needs some background work. Okay. So, we have to define this concept of restriction, okay, restriction of a function, and this restriction of a function is going to be very important as we move in this course, okay, because there are other topics that we would be discussing later on, and they would crucially depend they would crucially depend on this idea of restriction. Okay. So, let me define what we mean by restriction of a function. So, let f be a function from 0 1 to the power n to 0 1. Okay. So, before proceeding with the definition of restriction, so the definition is mathematically it might seem a little complicated, but let me give you the idea. So, the idea is very simple. So, I have a function on n variables, right. Now, suppose if I decide to fix some of the variables. Okay. So, between these n, let us say I pick some subset of the variables and I say that okay, these fixed variables will go to some fixed inputs. Okay. So, they will go to, some of them will go to 0, some of them will go to 1, and only the remaining variables are free, in the sense that they are actually variables, they can actually take a value either 0 or a 1, and depending on that the function is evaluated. Okay. So, that is what is called a restriction. Okay. So, we take a subset of the variables and we map them to either 0 or 1, and only the remaining variables are free. Essentially, that is the idea of a restriction. So, let f be a function on n variables over, let us say, the variable set x. So, I am just giving a name to the input variable set x1 up to xn. Okay. Let y, which is equal to y1 up to yl, be a subset of x. So, each of these y i's are some x j's over here, okay, and I have some L many of them. So, the idea is that these y many or this set y will remain free and the remainder I will fix them. Okay. Now, let z be equal to x minus y. So, this is the z that I will be fixing, a restriction second, let me see what is the terminology, sigma from z to 0 1 is the function. So, I will call it f sigma on the variable set y 1 up to y l, which is f of x k 1 up to x k n, such that if x k I is equal to y j, or j if x k I is the jth element of y and x k I is equal to sigma x I if x I is not in y, basically if it belongs to z. Okay. So, essentially I look at all the variables now. Okay. So, among all the variables, if I have a variable which belongs to the set y, okay, then basically it is I mean it is just a free variable, and if it belongs to the set z, then I will set it to sigma of that quantity. Okay. So, this restriction which is mapping this set z to 0 or 1. Okay. Now, what? No, 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 this is y l. Yeah, this is y of l. It is restriction, this is a notation for restriction. So, f restricted to sigma, this means. So, the basically the idea is that f behaves exactly the same, f restricted to sigma behaves exactly the same as f on the inputs of y, and on the inputs which are not in y, that is the inputs which are in z, it takes the value sigma of this. Okay. That is again the idea. Now, what else do I have to define? Okay. A sub function f restricted to some sigma is any function with domain of sigma being x minus y, okay, a sub function on y f sigma. Okay. So, basically what this is saying is that if I take any y, so any sub function on y is basically a function sigma on this domain x on the domain x minus y.